Area practice problems. Example 3. Find the area in the first quadrant bounded by f of x equals sine of pi x and g of x equals 8x cubed. Let's get a look at the graph of this f of x function, and then we'll get a look at what g of x looks like. And we see that g of x and f of x actually have area enclosed between them in both the first and the third quadrants. But of course, in this problem, it's very specific that we're to look at the area in the first quadrant. So that's the area we're trying to determine. It looks like there's an intersection at 1/2 comma 1. Just because it looks like there's an intersection, it doesn't mean there necessarily is. We could show algebraically that there must be an intersection there. However, we could also verify this on our calculator. So let's go ahead and put the sine of pi x on y1. And then for y2, we'll enter 8x cubed. And then let's look at the window here and think about making the window mirror basically what we have here. So we'll go from -1 to looks like about a half there, maybe a little bit bigger than a half. We'll go out to 1. And then for the y min and y max, we'll do -1 and then just a little bit bigger than 1 at 1.5 for the y max. Taking a look at the graph here, what we're going to do is verify that we've entered these things properly, and then what we're going to do is we're going to use the intersect feature. So that's second trace. Pick number 5 off the list. Now, intersect is designed to find the closest intersection. So I'm going to move off to the right here, and I'm going to seek the intersection there. And sure enough, it's at 0.5 comma 1. So that's good information. So now what we'll do is we'll kind of zoom in on this area in the first quadrant. And the first time we solve this problem, we're going to do it with vertical slicing. So we've got identifiers there for f of x and g of x. And we know that there's an intersection there at 0, 0. And we just verified 0.5 comma 1 is our other intersection point. So now I'm going to sketch in a vertical slice. I'm making it rectangular. I know it's not a perfect fit, but keep in mind that as I make these rectangles thinner and thinner, the error in the approximation by rectangles becomes smaller and smaller. So even though the rectangle doesn't perfectly fit in there, I can think about the dimensions of that rectangle. So how tall is that rectangle? Well, that's just the difference between the y value on the red curve and the y value on the blue curve. So that's f of x minus g of x. What about this dimension? Well, this dimension is supposed to be tiny. I've drawn it large enough so I could see it, but that right there is the differential of x. And I believe that if I multiply these two dimensions, that'll give me the area of the rectangle. Now, the rectangle itself is not representative of all the area, but if I made a bunch of rectangles like that and added them all up, then I would get the total area that I've shaded. So I'm going to call this the differential of the area of the region. And by differential, I mean a tiny little bit of the bigger area. And that can be found by multiplying its two dimensions. There's the height of the rectangle and multiply by the width dx, like we said before. Now, this is where the calculus magic comes in. What we're going to do is we're going to integrate this little bit of area or sum up all the little bits of area. And of course, that'll give us the total area. And so we're going to be summing up all of the products that look like f of x minus g of x times dx. The only thing I got to think about now is what are going to be my limits of integration. And those are going to be the x values at these ordered pairs. So everything in this integral The integrand is in terms of x. The differential is in terms of x. And then my limits of integration are going to be values of x. So everything in the integral in terms of x. Now to evaluate that, since I've entered them on my calculator as y1 and y2, I can refer to those calculator names and get the estimate from the calculator at about 0.193. So I'll conclude that the area of this region is about 0.193. It's not that difficult to show that this area can be found as an exact value. So it might be a good exercise for you to start with this integral, and then by using the fundamental theorem of calculus, find the exact value. I claim it's 1 over pi minus 1/8. And if you're struggling with that, why then I've got a link in the description to a written out step-by-step process for you to follow. In any case, our purpose here is to show that if we do it by vertical slicing, then we get the same area as if we do it by horizontal slicing. And when we're thinking about horizontally slicing, well, we need to rearrange our equations here so that instead of them outputting y values, they output x values. So how are you going to get that pi times x out of the sine function? Well, of course, what you're going to do is use the inverse sine function, and that'll isolate pi times x. And then what you'll do is you'll divide both sides by pi, and so we can say that x is equal to the inverse sine of y divided by pi. Similarly, we're going to rearrange the g of x function. So it currently says y equals 8x cubed. Following the order of operations, if I knew the value of that x, isn't it true that the very first thing I would do is cube the x? And then after that, I would multiply by 8? Yes, that's exactly right. So what I'm going to try to do is undo those operations in reverse order of operations order, which is to say, first I'm going to undo multiplication by 8, divide both sides by 8. And then to undo the cubing, I will take a cube root on both sides, and then I'll have x all by itself. So that's a good formula for g of x, but rearranged so that it solved x in terms of y. So when I'm thinking about the red curve and the blue curve here, I want to slice it horizontally this time. And as I do, I want to think about, well, what's the length of that rectangle? And that's going to be the difference between the x value over here on the blue curve minus the x value over here on the red curve. This g of x and f of x, by the way, are both equal to y, or outputs. So those labels aren't that helpful anymore. Instead, what I've got to do is I've got to think in terms of what's the x value on the blue minus the x value on the red. The reason I'm subtracting in that particular order is because I know that larger x values are to the right, and I'll take a larger value and subtract a smaller value. That'll give me a positive difference for this length here. And then what about the other dimension of the rectangle? Well, that now is a little bit of the y, or dy. So to get an expression for this little bit of area, I'm going to have to take the difference between the x value from the blue curve and the x value on the red curve. I'm going to have to take that difference and multiply it by dy. The area of the region then is going to be found by integrating this little bit of area I've computed. And that means summing up all the areas. And so I'm summing up all the objects that look like the area that I just computed. And now all that's left is to go after the limits of integration, which in this case are y values 0 to 1. Back on my calculator, I'm going to evaluate this integral. So I enter it 0 to 1, cube root of y over 8 minus inverse sine of y over pi, and this is with respect to y. We get essentially the same result that we got before. At least it's the same result to 4 digits after the decimal. And remember, in this course, the standard is, unless otherwise specified, your answer should be given to an accuracy of 3 digits after the decimal. You might wonder, why are we getting different numbers here after the fourth digit after the decimal? That's because the calculator is not doing calculus. Instead, what it's doing is it's doing an approximation. And so the approximation is imperfect, and we can see that when we set up the integral in two different ways, then we get two different results. But they're not that different, not significant enough to bother us. Thank you for watching.